Hello grade 10. Let's look at electrostatics. I know we've moved past this, but I've now got the software, so let's just talk about electrostatics. Now the word electrostatics is made up of two parts, electro and static. So static, if something is static, it means it's not moving, it's standing still. And electro has to do with charges. So electro, statics, standing still charge, electricity, moving charges. So electrostatics are static charges. And the largest form of static electricity that we know about is actually a lightning strike, because lightning strikes are actually caused by static electricity. You're supposed to learn that in grade 9. All the clouds rub together and charges build up. So in order to have static electricity, you have to get charge on the surface of an object, and the object always has to be an insulator, okay? And this thing charge, it's just a property of matter, like something can be heavy or something can be light or something can be dense. It's a property of an object, and all of this charge is actually derived from electrons. To some extent, electrons actually run the world because they are in charge of all the chemistry experiments, they're in charge of our electricity, they're in charge of all sorts of things. So electrons are charged and they are in charge. So charge is a fundamental property. Fundamental means it's just existing there. So some things can experience electrical forces and some things can create electrical forces. So how do we get static electricity, and on what do we get static electricity? We get static electricity on things that are insulators. So we need to know what's the difference between insulators and conductors, and we briefly discussed this with the properties of matter. So if you are a conductor, you can conduct an electrical current. Now metals over here are always conductors. Think about the copper wiring in the wall, it's conducting electricity. Remember, the valence electrons are the electrons are in the outermost shell. In the metals, they form that metallic bonding where there's the lattice, where there are protons all locked in place, and the valence electrons in the outermost shell can move around. They are delocalized. Sometimes we call them a sea of delocalized electrons because they can move around like water in the ocean. So it's a sea of delocalized electrons around proton cores. So these metals can conduct charge, and some non-metals can also conduct charge because they have loose valence electrons. And graphite in your pencils, which is made out of carbon, is one of them because it's got an interesting atomic structure that's different from diamond and different from those buckyballs, and that's why graphite pencils can conduct electricity, because they do have some delocalized electrons. And conductors offer little or no resistance to the flow of charge. So obviously metals vary. You know, when you do electricity experiments, there's nichrome wire, which has got a high resistance as compared to copper, which is in all our walls because that's got a low resistance. So a conductor has low resistance to the flow of charge. This flow of charge is moving electrons. Little negatively charged electrons are the flow of charge. So then in comparison, an insulator cannot conduct an electrical current, okay? The electrons are not free to move around in the sense that they can go in a specific direction. So the electrons can't flow, and most insulators are non-metals like plastic, perspex, which is a see-through kind of plastic, Teflon. This Teflon is also PTFE, so if you've ever been a plumber, that white tape that plumbers use is Teflon. Teflon's also what's inside your frying pans to stop your eggs sticking to them, things like that. Porcelain is very good fine china pottery, and rubber, obviously, like the rubber of your car tires and your eraser and stuff. So all of those things are insulators, and usually they can't have flow of charge. And then carbon, the one that I talked about in graphite, is an exception to the general rule that non-metals are insulators, except for diamonds. Diamonds actually can't conduct electricity because it's got such a nice secure bonding structure that none of the electrons can move around. So basically metal conductor, non-metal insulator. So the world is divided into two types of charge, positive and negative, okay? The positive charge is on the protons, the negative charge is on the electrons. Now, in this whole topic, you have to remember every single thing on the planet is made up of millions and millions and millions of protons, neutrons, and electrons. We're not worried about the neutrons now in this. but we are worried about the protons and electrons. Now, I always tell people protons are like those people on My 600-Pound Life. If you've ever watched that show on TV, you know those people don't move around very easily. So protons are like people in My 600-Pound Life. They don't get around much. In fact, they don't get around at all unless you're in the Large Hadron Collider in Switzerland trying to make nuclear bombs or something like that. So protons are doing nothing. Little whizzy speedy electrons, they are the ones that do everything. So only electrons can move. So what happens is, obviously we're not going to draw 1,000,000 electrons and 1,000,000 protons. If you look at this neutral object, we have 1, 2, 3 positive charges, 1, 2, 3 negative charges. This is a neutral object. There are equal numbers of positive and negative charges. This object, on the other hand, is positively charged. If you look, 1, 2, 3, 4 positive charges, 1, 2 negative charges. So there's more pluses than there are minuses. This is positively charged. In order to become positively charged, it lost an electron. Do not touch the protons. This object lost an electron because only electrons can move. On the other side of the page is a negatively charged object. Look here, 1, 2 positive charges, 1, 2, 3, 4 negative charges. So this one has gained electrons from somewhere. You don't know where it's gained it from, but it's gained electrons. So this one is negatively charged. It's got all its protons it started with, but somebody's added more electrons. Okay, so we have things that lose electrons and things that gain electrons. And if you are neutral, we use this word net. I don't know if you're used to this word from EMS, but this word net, no net, it means that basically you are equal. There's not one thing that's more than the other thing. So we use this word net a lot in physics. There is no net electrical charge. That is, there are the same number of positive and negative charges. So we could say, if we looked at this object, there's 6 charges in this object, but this object has a net positive charge because there are more positives. And this object here has 6 charges altogether, but there is a net negative charge because inside the 6 there are more negatives than positives. And this one has no net charge because there are the same number of positive and negative charges. So what happens is, and you know this is one of my favorite sayings, like charges repel, unlike charges attract. So one of the things that they like to ask you about here, and sometimes these diagrams are a little bit misleading, but they're using it to try and illustrate things to you. One of the things that happens is if an object has a charge, we know that like charges like charges repel and unlike charges attract. So then sometimes they say to you, what's going on? This charged object over here is exerting on a force on something that is neutral. And this is because you have to remember the nature of electrons. So charge is coming from electrons, and electrons are small and whizzy and can move around. So here comes a little charged rod. Here's the object, and all the charges are evenly dispersed, okay? And then along comes this rod, and it's positively charged. So opposite charges attract, and so all of the little whizzy electrons that are free to move to one side of the object. And then you've got a positive charge and a negative charge, and opposite charges attract. So this is called inductive attraction. There's induction going on here. This rod has induced a movement of the electrons to one side of the object, and that is why it can exert a force. It's not it happens as a result of charges moving internally in here. But if we were to count 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. There are equal numbers of charges in this object. This object is still neutral, but some of the little electrons have whizzed over to the other side, hence the attraction. And this is a favorite test question that you have to explain. Okay. Now we need to talk about what the charge is like. The force of attraction or repulsion between two charged objects it gets stronger when the objects get closer. Okay, so now think about, we've all experienced electrostatics because we've all been zapped by static electricity. So like in winter when the air gets dry and we walk on the carpet, when we're a meter away from the door handle doesn't give you a zap, but the moment you get close to the door handle, you get zapped. Okay, so obviously the force of attraction increases when the charged objects get closer, and the force of attraction increases when the charges on the objects increase. So a good example of this is lightning. You've seen how much damage lightning can do with houses burning down and trees being destroyed and things like that. That's all done by electrons. But if you think about it, the sky's pretty far away. How did that lightning bolt get to Earth? The objects didn't get closer, but there were so many charges up in the clouds that all of a sudden the charges were attracted to the Earth. So this is what happens. The bigger the charge, boom, you get a lightning bolt. But if you just, don't rub your static blanket too much, you don't get so zapped because there's not a lot of buildup of charge. So this is a force of attraction, and next year we're going to do sums with these charged objects, something to look forward to. Okay, so let's look at the 3 ways that objects can be charged: friction, contact, and induction, which is also the same as polarization. So do we know what friction is? If you don't know what friction is, rub your hands together. Okay. So the next thing we need to know about charge is that we measure charge in coulombs. Now when we get to electricity, you see the same coulombs in electricity. This is an SI unit. It's named after Mr. Coulomb, and it's got the symbol Q. This is a symbol you need to learn, and a unit you need to learn. No unit, no mark. So scientists have worked out, because they've been at this for a long time, what is the charge on an electron. They've given it a number, and it's minus 1,6 minus, because the charge on an electron is negative, minus 1,6 times 10 to the negative 19 coulombs. So you can imagine here that this is a pretty teeny tiny charge. That's why we need a lot of electrons to get a whole coulomb. Okay, if you put this number as 1 over this number, the inverse, you get this really large number of electrons, 10 to the power of 18. So you've got to move this comma 18 decimal places. It's a really big number. And that is how many electrons give you 1 coulomb of charge. No, I don't know why the number is like this. It's just how it happened. Okay, so now let's talk about the way we can charge objects. You can charge an object with friction. So electrons are literally physically picked up from one object onto another object. Now, they will often give you objects in test. They're 2 random objects. Don't worry what the objects are, worry what the electrons are doing, okay? But we do know that if you wear certain clothes, you're more likely to get a static shock. So like for instance, in winter in my bucky with the car seat covers, if I wear exercise pants, I'm more likely to get an electric shock than I do if I wear cotton jeans, okay, because of the material that the 2 of them are made out of. So there's a thing called a triboelectric series that determines, are you going to become positively or negatively charged when you are rubbed with something else, okay? But we just need to know this thing exists, and it's called the triboelectric series. We don't actually need to memorize the list that's on the other page. But what happens is the polarity and the strength of the produced charges depends on the materials. So like if you go to places where there's lots of carpets and the air is quite dry, you'll find some carpets. You walk around like supermarkets in Joburg in winter, you walk on some of the carpets and boom, you get zapped on the shelves, you get zapped everywhere. And then you walk on somebody's porcelain tiles or ceramic tiles on the floor, you don't get zapped at all. So the polarity and strength of produced charges depends on the materials, because I hope you realize that your feet walking on the carpet are providing a source of friction. So this is the triboelectric series. These are things that are more likely to get a positive charge, and these are things that are more likely to get a negative charge. So the brief one, rubber, polyester, vinyl, silicon, and Teflon are more likely to gain electrons, and nylon, wool, and cotton are more likely to lose electrons. So if you've got a piece of wool and a piece of, say, vinyl, which is a plasticky kind of stuff, and you rub the vinyl with the wool, all the electrons would jump off the wool onto the vinyl. Okay, so now what is the next way that you can get charged? So say I've got one charged object. Say I rubbed my ruler on my hair. I do like to demonstrate this in class. You can demonstrate this yourself if you have hair that doesn't have oil in it. And if you've got long straight hair, it works the best. So if you get a charged object, you charge an object by friction, and then you come towards an uncharged object. The two objects are going to share the charges. Electrons like to be shared. Nobody actually likes, and realize you can't write likes in the test. I'm trying to explain this in a way that is understandable. Okay, so what happens is if you've got a charged object and it touches an uncharged object, little electrons are going to move. So for instance, here it says to you, if a positively charged object touches a neutral object, electrons will flow from the neutral object onto the positively charged object until both objects have the same charge. Now you're going like, look here, positively charged object. This positively charged object is missing electrons. Yes, it's missing electrons, but bear in mind there's like a million other electrons still sitting on that object that can move, and so now they are unbalanced, and this neutral object here has also got a million electrons, so the neutral object is going to give its electrons to the positively charged object because this one's got more electrons. So if you bring two positively charged objects together, they're still going to share electrons because even a positively charged object has still got a million little electrons lurking in its self. Okay, so the moral of the story is here, electrons on charged objects like to be shared. They will flow between two objects until both objects have the same positive charge. So here are these funny little diagrams that you can look at to explain this. For example, okay, here are my two objects, and they like to draw them on these round balls or spheres or something. This object has got a charge of minus 3,6 coulombs, so it's got a lot of excess electrons, and this object is neutral. So if this object touches that object, the electrons want to be shared. So at the end of the day, if you separate them, both of these two objects will end up with a negative charge, and if you're good at mental arithmetic, you'll know that this divided by 2 gives you this. Okay, minus 3,6 divided by 2 gives you minus 1,8. So the electrons, if you count all the electrons in this object and all the electrons in this object at the very beginning, and you count all the electrons in this object and all the electrons in that object at the end, there will be exactly the same number of electrons at the end as they were at the beginning before they touched. But after they touched, these two have going to share the electrons so that they've both got the identical charge. So that's the first example, and this is easy to understand because there's a lot of extra electrons on here. Now on this example, we've got a positive charge here. This has got a positive charge of 4.8 coulombs, okay? And it's now touching a neutral object. Lots of electrons on here, but more protons than electrons, an equal number of protons and electrons. These two touch, okay, in this next picture, and the electrons flow from the neutral object to the charged object, but they don't overflow, they flow until these two end up with the identical positive charge. So 4.8 plus 0 divided by 2 gives you 2.4. The same way here, minus 3.6 plus 0 divided by 2 gives you minus 1.8. Now the third kind of charge is induction. Induction is a method of charging where the one object doesn't touch the other object. So this is often what comes up in the questions. Here's my little rod, it's full of electrons. Here's my sphere that is neutral, but the electrons can move inside the sphere because electrons are small and whizzy. So as you bring the negatively charged rod here, like charges repel, and all these little electrons are chased away to the other side of the object, leaving behind the boring, big, stuck in their place protons. And now you're in the situation, once the electrons have been chased away, that there's positive charges over here and negative charges over here, and opposite charges attract. So for instance, there's an example of a diagram here, A, B, C, D. How you can charge an object without touching it. Okay, these two insulators, they're on an insulated stand, but there are conductors up top here, and here are insulators. And the reason there's an insulator here is if there isn't an insulator here, any charge that ends up on here flows down into the table. So here we've got two charges with equal number of protons and electrons, and then here comes a rod with a negative charge on it. These two are touching each other, so electrons can flow between the two of them, okay, because they're conductors on an insulated stand. So here comes this ebonite rod, and the whizzy little electrons that were over here get chased away, and they can get chased away far enough that they end up on the other ball. So while you're still chasing the electrons away, you move this sphere away, sphere B, you move sphere B away from sphere A. And now look what's happened. Because the electrons at this stage moved from A to B, when you separate them, they stuck on B. They can't get off here because they can't get off the insulated stand. And poor little A over here, he's lost all of his electrons. Well, not all of his electrons, but he's lost a bunch of electrons. And he's left positive, and B is now left negative. But you never touched these two with a rod. You just use the property of induction to cause this charge. Now there's one more thing that goes with this. Water is polar. Okay, we talked about this when we talked about bonding, and I've mentioned it briefly. So if we have a water molecule over here, this thing here is representing the electron cloud around the outside of the water molecule, and this electron cloud is unevenly distributed because this oxygen nucleus is full of protons, and this poor little hydrogen's only got one proton in its nucleus. So this oxygen atom, its protons in its nucleus are saying, electrons, come to me, come to me. And the electrons are pulled in this cloud. You see where it's gone red here? The electrons are pulled towards the oxygen atom, and this leaves this edge of the hydrogen atom slightly positive because the proton is sticking out because the electron cloud's been pulled sideways. The same with this hydrogen atom. The electron cloud's been pulled towards the oxygen by the protons in the oxygen nucleus because opposite charges attract. So a polar molecule like water, we'll learn about some more next year, they have a slightly positive side and a slightly negative side. It's not as strong as the charge on an ion, but it is still a charge. By the way, if you want to work out polarity, you use the electronegativity. Remember electronegativity from term 1, you use the electronegativity on the periodic table. So what happens is, if polar molecules get near something that's got a charge, they can move to be attracted to the charged object because the opposite charges want to be close together. So this is just another example of what it looks like, the polarization, another representation of it. They like to use this little delta to show you that it's a partial charge. And this is actually what happens to water molecules when they meet each other. This oxygen is slightly negatively charged, and it has a force of attraction, an intermolecular force of attraction to other water molecules, but they're attracted towards the slightly positive side. So if you get a balloon and you charge it by rubbing it on your hair, so this balloon has been charged by rubbing it on your hair or on a piece of cloth or something like that, and then you turn on the tap, so there's a tiny thin trickle of water out the tap. You can actually bend the water with the balloon, and that's because inside this stream of water all the little water molecules are lining up so that their opposite charges are being attracted to whatever is charged next to them, and then the stream of water bends. So it's quite an interesting thing to do, and if you've got a balloon at home and something to charge it with, you can prove this. Okay, this picture here is of a schematic diagram of a gold leaf electroscope, And a gold leaf electroscope has got two little leaves on the bottom. Excuse me. Excuse me. A gold leaf electroscope has got two little gold leaves on the bottom. It's not really gold, but it's just something that's gold colored and is conductive. And if you bring something charged next to it, these can move easily because they're very light. So we use electroscopes to check charge. There's one in the lab, and if we ever get back to school, I'll show you. So this is how a gold leaf electroscope works. By induction, you bring the charged rod here. It sucks all of the little electrons, well, in this case, it's pushed the electrons away here. This charged rod is negative, and it pushed all the little electrons down into the leaves to try and be, because they were repelled by this negative charge on the rod. This left the protons up here, so there's a bit of attraction down here. But now there's too many electrons down in the bottom of the leaves, and the leaves need to separate. So this thing is in this special bottle to insulate it, because if you've got a conductor, these leaves are conductors, they have to be insulated, because if a conductor is not insulated, all the charges go to earth. I'm going to stop here now because sneezing.